Hey everyone! Today, we're doing more than just learning calculus. We're actually going to build a powerful toolbox. Together, we are going to forge the tools you absolutely need to understand some of the most fascinating functions in the universe. So, let's get right into it.
You know, when you think about it, our world is just full of cycles. Everything from sound waves to the planets orbiting the sun to the rhythm of our own heartbeats. It's all waves and oscillations. But how in the world do you measure the instantaneous rate of change in something that's constantly curving and moving like that? Well, that's the big question we're answering today.
To get a handle on these kinds of problems, one single tool just isn't going to cut it. Nope, we need a whole kit. So that's our mission for this explainer. We're going to assemble the ultimate differentiation toolbox, piece by powerful piece, starting with the absolute essentials.
Okay, first things first. Every great toolbox starts with the basics, right? And in the world of trig derivatives, that means getting to know the beautiful, totally interconnected dance between sine and cosine. These are your foundational tools.
Now, what's so cool here is how perfectly the formula on the left and the graph on the right tell the exact same story. I mean, look at that sine wave. Wherever its slope is steepest, either going up or down, the cosine wave is at its peak or its valley. And wherever the sine wave flattens out at the top or bottom, the cosine wave hits zero. They are in this perpetual dance, where one is literally describing the motion of the other. It's amazing.
And here's the part you really need to lock in. It's a perfect, predictable cycle. Sine's derivative is cosine, okay? Cosine's derivative is negative sine. Then negative sine's derivative is negative cosine, and that brings us right back around to sine. It's this perfect four-step loop. Honestly, it's one of the most elegant relationships in all of mathematics.
All right, with our core tools in hand, it's time to upgrade. Let's add some specialized attachments to our kit. These are going to let us handle a much wider range of trigonometric functions, and with way more ease.
And bam, just like that, our toolbox gets a major power-up. Now, since all of these functions, tangent, secant, all of them, are really just built from sine and cosine, we could derive these every single time. But for our toolbox, no way. We just want to have them ready to grab and go. The derivative of tangent is secant squared, derivative of secant is secant times tangent. You get the idea.
So what's the point of a shiny new tool if you don't use it, right? Let's take this function for a spin. We've got two parts here. For the first term, cosecant x, we just reach into our toolbox and grab our new cosecant tool. Done. For the second part, x tan x, okay, we've got to combine things. We use the product rule along with our new tangent tool. See how that works? We can combine our tools to quickly break down what looks, at first, like a pretty complicated problem.
So far, we've been dealing with pretty straightforward functions. But now, it is time to unveil the master key, the multi-tool, the single most important power tool in our entire differentiation kit, the chain rule.
I mean, think about it. What if you have the sine of a squared function, or the cosine of another trig function? Our basic tools just can't handle functions that are wrapped up inside of other functions. It's exactly like a set of those mathematical Russian nesting dolls. How do we get to the center?
So this nesting doll idea, it's got a formal name, of course. It's called a composite function. It's just one function, let's call it g, that's living inside of another function, f. And really understanding this structure, that's the key that unlocks the power of our next tool.
And this is the solution. The chain rule. It is so elegant. It basically tells us, work from the outside in. First, you take the derivative of the outermost function, the biggest Russian doll, and you leave everything on the inside alone. Then, you multiply that result by the derivative of the next layer in. It's a chain reaction, linking the derivatives of each layer together one by one.
And hey, the chain rule is not just for trig functions. Not at all. Look at this example. By rewriting that fraction as a negative exponent, we can clearly see it's a composite function. The outer layer is the power of -2, and the inner layer is the polynomial. We just apply the chain rule, and a problem that looked really intimidating becomes totally straightforward.
Okay, we have built the toolbox. We have our foundation tools, we've got our specialized attachments, and we have our master power tool. Now it's time for the masterclass. Let's bring it all together and tackle a truly complex function. All right, this is it. The final boss. Just look at all the layers here. On the very outside, we have a power of 4. Tucked inside that, there's a cosine function. And then way down in the very center, we have a polynomial, 7x squared plus 1. That's 3 layers deep, a triple-decker Russian doll.
So how do we crack this thing? We just apply the chain rule step by step. We work from the outside in. So step 1, deal with that power of 4 using the good old power rule. Step 2, multiply that by the derivative of the next layer, which is cosine, and its derivative is negative sine. Step 3, multiply that by the derivative of the very innermost layer, which is just 14x. See? It's just a chain of multiplication, one link at a time.
And here is the beautiful result. You can see exactly how each step of the chain links together. The power rule part, the cosine derivative part, the polynomial derivative part, all of them working in perfect harmony to just dismantle the problem. So, what does this all mean? It means you've got the tools now. You've seen how they work, from that basic sine-cosine dance all the way to the absolute powerhouse that is the chain rule. You now have the ability to analyze the rate of change for incredibly complex systems. The only question left is, what will you choose to analyze?